Hey everyone, here in this video we will try to learn about the concept of dynamic braking and the very process of load box testing as performed in Jamalpur workshop. To begin with, let's introduce ourselves. I am Ankur Charkrawarti from SCRA 2014 batch and myself Rajat Kumar from SCRA 2014 batch. The Indian Railways will become the growth engine of nation's Vikas Yatra, as said by our Prime Minister Narendra Modi. So let's have some focus on the video. Dynamic braking. So let us understand what is dynamic braking. Dynamic braking is the use of electric traction motor of a railroad vehicle as generator when slowing the locomotive. It is termed rheostatic if the generated electrical power is dissipated as heat in brake grid and regenerative if the power is returned to the supply line. Dynamic braking lowers the wear friction based braking components. And additionally, regeneration can also lower energy consumption. Dynamic braking can also be used on rail cars with multiple units, light rail vehicles, trams, and PCC or streetcars. This is a circuit which explains the working of dynamic braking. Traction in this circuit, we can see that traction motor acts as a generator and generator acts as an exciter, and the power of motor is dissipated through grid and also drives the blower. What actually happens is that when braking, the motor fields are connected across either the main traction generator, that is the diesel electric locomotive, or the supply, which is the electric locomotive. And the motor armatures are connected across either the brake grids or the supply line. The rolling locomotive wheels turn the motor armatures as we can see in the diagram, and if the motor fields are now excited, the motors will act as generators. So during dynamic braking, the traction motors which are now acting as generators are connected to the braking grids, that is the large resistors, and which puts a large load on the electrical circuit. When a generator circuit is loaded down with resistance, it causes the generators to slow down their rotation. So by varying the amount of excitation in the traction motor fields and the amount of resistance imposed on the circuit by the resistor grids, the traction motors can be slowed down to a virtual stop, that is approximately 3 to 5 miles per hour. Effect of dynamic brake at different speeds. Around zero speed, the braking torque remains almost zero, and by using dynamic brake, we cannot stop any loco. At the speed up to 35 to 40 km per hour, the dynamic brake is directly proportional to speed. This is because the excitation speed of locomotive is designed such that the generator current remains constant, and hence the field strength of the traction motor also remains constant. But when speed exceeds 35 to 40 km per hour, this is inversely proportional to the speed, and as the speed field strength is made reduced successively by the reducing the current. This is a circuit diagram showing the connections of 6 traction motors with the grid during the dynamic brake application. Changes occurred in circuit during dynamic braking. BKT comes into braking mode, which brought all traction motor field in series, above series across generator, traction motor armatures across braking grid and blower motor. Hence, all these operate when there is single BKT and single reverser. Energizes the BKR, which makes engine speed of 4 notch. Replace engine speed signal with braking control signal at mixer. Set up BKCP for increasing or decreasing the signal at mixer circuit. If the generator is DC type, this is converted into differential compound generator for more stability. This figure shows us that dynamic brake, how it is actually used in the trains. Earlier the left one was used and now the right one is used. In the left one we can see that there are three positions. There is a selector, there is a reversal, and there is a notch. And in the right one all have been clubbed into one. And what actually happens is that as we go on decreasing the size of bees, there is a sequence for it, and then the rheostatic principle applies, and accordingly, the magnitude of the amount of brakes applied goes on increasing, and the speed goes on decreasing accordingly.
This graph shows the motor armature current versus locomotive speed. In this graph, we can see that initially with the speed, the dynamic brake application increases proportionally. Around 35 to 40 km per hour speed, it is maximum. But as speed increases, the dynamic brake application decreases proportionally.
Coming to the advantages of using dynamic braking in a loco. While using traditional frictional braking, the wear on the wheels and the brake shoes is often too high. It is well known and famous that whenever there is an engineering, there is a way. So dynamic brake comes with a solution as it also reduces the noise and the life of the locomotives is increased, and it can be applied whenever a train is moving to down gradient, and it is also quite economic in nature. And higher the speed of the train, the better is the brake application. Coming to the process of load box testing, a very well-known test in Indian Railways. So, what is load box testing? Is it an art or is it a science? It is a very famous question, and it is often said that art without engineering is dreaming, and engineering without art is merely calculating.
Let me introduce you to the load box testing. This is a test to check the capability and performance of the engine by simulating the actual working condition of the locomotive at rated output in static condition. Load box examination is carried out in diesel locomotive to determine the generator alternator output and the gross engine power by simulating the actual working condition of the locomotive at rated output in static condition. In this, the output of generator is connected across a set of resistance instead of connecting it with the traction motor. This examination is carried out before and after major schedule (POH) as well as major non-scheduled jobs on engines such as TSC replacement, etc. During load box test, the output of the engine is measured in terms of electrical parameter, which is volt and ampere. In this, the output of the generator is connected across a set of resistance. Instead of connecting it to traction motor, the output of the engine is dissipated in terms of heat across the resistance during load box test.
Coming to the three W's: why, when, and where. Whenever we do it, when the engine is not giving us the desired output, we have to check it out whether all the systems are functioning properly or not, and whether any problem is connected to any system or component. We do it after every new manufacturing, before and after major repairs, before and after any major schedule, and to diagnose any specific problem. It is conducted on the specific load box test area in the shed or in the workshop. In case of GM locos and the latest microprocessor controlled locos, the facility of the load box test exists within the loco itself.
There are two types of load box testing. First one, grid resistance load box testing. Second one, water resistance load box testing. So let us understand the differences in between them. Water resistance load box testing. Load resistance can be varied at infinite stages. Hence, a continuous HP curve can be plotted through this. In grid resistance, load resistance can be changed only at limited stages, 3 to 6. Hence, a complete graph cannot be plotted to understand the complete behavior of output. In water resistance, load resistance can be changed during loaded condition. In grid resistance, to change the load resistance, the grid type, the locomotive required to be stepped down to lower notches as done in the load test interrupted and many times resistance required to be changed. In water resistance, water load box can be conducted for a longer duration because of better heat dissipation facility. But whereas in grid resistance, load box cannot be conducted for longer duration as it gets heated up quickly causing hazardous environment and gives erratic reading. In water resistance, it requires permanent establishment to set up water load box, hence cannot be shifted easily. But in grid resistance, it is handy and can be shifted with lesser efforts.
Now, the procedure of load box testing that is being followed in the workshop. The first step involves preparation for starting of the loco. The second step being pre-inspection. The third one is cranking. The fourth one is notching up, and the fifth one is a preload test that is performed. And now this is the chart that we have obtained from the actual place where it is conducted in the Jamalpur workshop. And various parameters are measured in it. Some of them being the AC voltage, exact voltage, reference voltage, ECRTS voltage, reference current, battery voltage, auxiliary voltage, and so on. Now, the various performance parameters that are to be taken care of while we perform the load box testing, some of them being exhaust gas temperature. Now, if we have not to get exhausted, because if we don't get exhausted, we are not doing it right. So the ideal range for the exhaust gas temperature is 525 degrees centigrade to 600, and for the higher exhaust gas temperature can be caused by incomplete combustion of fuel, or maybe due to the higher inlet air temperature. That may be another reason. And the compression pressure, the ideal range being 400 to 440 pounds per inch. And the next is the booster air pressure, and the ideal range being between 1.6 to 2.0 kg per centimeter square. Firing pressure, which is the parameter directly related to the combustion of air and fuel mixture in the combustion chamber to develop specific HP of the engine. The ideal range for highly efficient turbo is 1650 to 1800, and for Alco turbo it is somewhat lower to 1450 to 1600 pounds per square inch. Now the fuel rack travel. What is the actual fuel rack travel? It is 30 plus minus 1 plus 1 or minus 2 mm, and the lube valve pressure at header it should be ranging between somewhere 5.3 to 6 kg per centimeter square. The tank is vacuum. The range being minimum crankcase vacuum in inch of water should be zero point 0.5 inches, and the turbo supercharger speed, which is the measurement of the extreme, it is of extreme importance to measure it because they remain in service ranging between 6 to 2 years without any maintenance. Higher turbo RPM indicates lesser service margin and higher pressure ratios, leading to the lower reliability as such. Exhaust gas appearance. The various colors can be obtained in the exhaust gas. Maybe it may be black, white, or grayish blue. All these indicate different types of deficiencies that are there. There should be no color actually.
This is a chart which lists the performance test parameter which should be matched during load box testing. And this is the curve between voltage and load current during load box testing. As said by Einstein, anything that counts may not count. Anything that does not count may count. Thank you.
Thank you.